Okay, hello everyone. Welcome again to my videos. This series dedicated at power system analysis. As you must remember, we are working with short circuit analysis, and we are extremely happy to today to run a practical session related with short circuit analysis and symmetrical faults. Okay, that is what we are doing today. In front of you, you can see the example 3.1. Okay, and this example is mainly dedicated that you can understand how to create the sequence networks and the Thevenin equivalence. Okay. In this example today, I would like to use a very simple power system. You can see over there are four buses over there, and as you can see, there are four buses, and the system is mainly one generator and one motor, and they are interconnected by coupled transformers. Um, and Okay, let's see. Here we have a generator. The generator is using a step-up transformer up to 138 kV and going to a transmission line. Then from the transmission line going to a step-down transformer, and from there going to a motor. Okay. This is the single line diagram. You can see that this system is quite interesting for asymmetrical faults because we have here the specific connectivity of each device. We can see that the generators, well, first, that the generator and the transformer T1 and T2, they have star connections, and those star connections are solidly grounded. I mean, there is zero impedance between the neutral point and ground, okay? And the other thing that you can see here is that the motor is connected between the neutral point and ground. Reactance, in this case, we are assuming this is 0.05 per unit on the database, on the base data coming from the nameplate of that mode. Okay? Imagine that previous to any fault, the system is unloaded. There are not load currents, and as consequence, we can assume that all the voltages are equal. In this case, we will assume that is equal to 1.050 degree. Okay. Um, Again, we are neglecting all the pre-fault currents. And the other thing that I want that you keep in mind is that the delta star transformer, there is a phase shift. And in this case, we are neglecting that phase shift. Okay. There are a couple questions in this problem. The first question is very simple. We need to create a plot, a drawing presenting the positive sequence and negative sequence network for this system. And then we want to reduce those networks using Thevenin equivalent model, and we will reduce this network based on the bus bar number 2. Okay. For basic reasons, we will assume that all the base are in this all the quantities per unit quantities are referred to the same base, and we will assume that base is 100 MVA. Okay, extremely simple. We want the network sequences network, and we want to calculate the equivalent Thevenin model, but all the Thevenin equivalent model for positive, negative, and zero sequence, they will come from the bus bar number 2 here, the bus bar number 2. Okay, let's start to do calculations here. And the first step is you must realize that per unit values of these generators, they are in 100. Per unit here is 100 MVA. Here at the transformer, again 100 MVA, and here at the motor, again 100 MVA. That means generators, transformers, and the motor, they don't need any per unit transformation. The only situation here is the transmission line. Why? Because the transmission line is defined, the reactants are, the sequence reactants, they are defined in ohms, okay? And we are interested to run calculations using per unit system. That means those ohms must be transformed into per unit system, okay? Let's start my explanation, very simple, sorry. And what we'll do first is, okay, we want to calculate the bases, okay? In this case, I will calculate straight away the bases for the impedance, and you must remember the equation. The base impedance, it depends of the square value of the voltage and the apparent power base. And we get here that the impedance base, in this case at the 138 area, this impedance is referred to 138 kV. This is 190.4 ohms, okay? The other thing that I will do by now is calculating the base current, but this base current will be at the voltage level of bus bar number 2, and that is 13.8 kilovolts, okay? When we run the calculations, is 4,183 amps, okay? Good. Next step. Well, the next step is that I told you that the transmission line have the impedance expressed in ohms, real units, and we are interested in running our calculations using the per unit system to take advantage of per unit system. We do that in power system. What we need to do is calculate the reactance, positive reactance, negative reactance, and zero reactance, all of them in per unit, and it's extremely simple. What we need to do is divide the positive reactance using the base that we already calculate. When we put the number together, positive and negative sequence, they have the same value, 0.105. And the zero sequence, you can see that is a bit bigger. It's probably more than 3 times or almost 3 times, 3 times specifically, 0.315, okay? Okay, right now we have all the reactants coming on the transmission line expressed in the same basis in per unit, and that is 100 MVA and 138 kV, okay? Positive sequence model, extremely simple, I love it. The positive sequence is extremely simple because we will use the model coming from the generator. This is the generator. We are using the positive sequence. In this case, this is the subtraction reactance of this generator. Then we have on the other side the motor. The motor, this is the subtraction reactance coming from the motor. That is the positive sequence reactance. Then we have two transformers, T1 and T2. And finally, we are using the reactance that we got for the positive sequence on the transmission line, okay? What is happening here? What is happening here is that I want to calculate the Thevenin impedance here, and I will do that later, but I would like to put the terminals over here. And the other thing that I am doing at this moment is that I need that you understand that if a fault is installed in bus bar number 2, I need that you understand that at positive sequence, we will have two contributions to the fault. One contribution coming from the synchronous generator to the fault in bus bar number 2, and one contribution coming from the motor going to the bus bar number 2. For that reason, I took the opportunity and I put those red arrows over there, indicating that they are two contributions mainly coming from two branches, one from the generator, the other one coming from the motor. And the other important thing here is that you must realize that in positive sequence, we have voltage sources, one voltage source representing the internal voltage of the synchronous generator, and one voltage source representing the internal voltage of this motor, okay? You will see voltage sources only at the positive sequence, okay? Okay, now it's time to create the model for the negative sequence, okay? Negative sequence is quite simple because it's quite similar to the positive sequence, okay? They are similar because we have here the transformer, we have the other transformer, we are using the same model for positive and negative sequence. The transformer has the same model. And for the transmission line, we are using, again, the model is the same for positive and negative sequence. The transmission line have the same model. Something that you must notice, now we are using the negative sequence coming at this generator, 0.17. You can see the data, and that is the data for negative sequence reactance. But there is not voltage source. And it must be clear to all my students that negative sequence cannot be produced by synchronous machine. That is the reason that we don't have any voltage source here. Same situation is happening with the motor. There is no possibility of creating zero sequence voltages. That is the reason that there is not a voltage source. Again, I am taking the opportunity here, and this is the push bar number 2, and what I am doing is I am including the terminals where later I will calculate a fault, but later also I will need the Thevenin impedance, okay? I am taking the opportunity, including two arrows over there, to define this is the negative sequence contribution coming from the motor, and this is the negative sequence contribution coming from the generator. Okay, nice. Next step, and probably the quite interesting here. The quite interesting here is let's talk about the zero sequence. Well, as you must remember, zero sequence is extremely important that you take in account the connection between neutral points and ground. Okay, it's extremely important because they will define the proper zero sequence model that you need to use in your zero sequence network. Okay, let's start here. We have a synchronous generator, and this is star connected. For that reason, it's very simple. There are no voltage source, but here we are using the zero sequence impedance of this generator. And you must remember from the data say that that is um, uh, 0.05, okay? 0.05, okay? Okay, good. And then we have a transformer, and that transformer is a step up transformer, and that step up transformer is delta start with the start solidly grounded. Okay, you must remember from my class about symmetrical components that if you have a delta connection, it's impossible having zero sequence currents. But on the other hand, here we have this grounding connection. This is a solid ground, and that is a possibility for zero sequence current to move through. That is the reason that we have this small keyboard here included in the representation of the zero sequence model for this transformer. Lines, we are using the zero sequence impedance of this line, everything fine here. And then we have a step down transformer, but in this case, we have star connected on the high voltage side, delta connected on the low voltage side, okay? What is the situation here? It's the same. If we have a delta connection, it's impossible having zero sequence currents moving in this line. And that is the reason that we have this open circuit here. But the solid ground at the star side, that allow me the circulation of zero sequence component. That is the reason that we are including this cable over here. You can see more details about this model if you watch my video about symmetrical components, okay? Finally, at the right hand side, we have the model for the motor. In this case, this is the reactance. This is the zero sequence reactance of this motor, and the connection is star connected with a neutral point that is connected to ground using a neutral reactance. In this case is 0.05 the reactance, but you must remember that this 3 is coming because we need to represent that this connection allow the circulation of 3 times the zero sequence. And that is the reason that we have this number 3 over there, okay? If you have any doubt about this, please feel free to drop an email and please feel free to make some questions, okay? Over there, I have included a short explanation, but the next step is I want to calculate the Thevenin equivalent model. And I believe all my students can see if I am interested on the Thevenin model here, there is a branch here and I need to switch off this generator. And there is a long series connection here when we switch off this generator. If we assume this generator is switched off and this generator is switched off, you will see that 0.20 is in parallel with this series. And that is what I am writing here. This 0.20J is in parallel with this big series connection. And that is the reason that we are adding all those reactants. And we calculate here we calculate over there the Thevenin impedance at bus bar number 2 for positive sequence, okay? Here you can see I create the positive sequence Thevenin model, and that model is the the Thevenin equivalent model for this positive sequence, okay? Now let's jump to the negative sequence. Negative sequence is extremely simple. You have here the circuit is similar. We create this circuit model a few minutes ago. Here they are the terminals where I want to calculate here the Thevenin equivalent impedance, okay? There are few changes in this diagram. You must recognize this is the negative sequence impedance of the motor, and this is the negative sequence impedance of the generator. Now we have a big series on this left-hand side, and that is in parallel with the 0.21 reactance coming from the motor. We put the number together, and voila, we have here a beautiful result, and that is the Thevenin equivalent model. This is the negative sequence Thevenin equivalent model of my system, okay? Very simple. Next step, let's go for zero sequence. Okay, few minutes ago, we create here, oh, something happened here. Something happened with the diagram that is not presented here. Okay, let's do the following, okay? Okay, negative sequence, very simple. You can see here I am showing you the negative sequence model that we create a few minutes ago. But there is, I think all of you can see my pointer here, and all of you can see that in this case, the transformer, the delta side, the low voltage side, is disconnected from the remaining components of this system. And as consequence, we can isolate the right hand side from the left hand side. And what I am interested here is to show you that at the end, for zero sequence, the only components that they are interacting with the zero sequence uh, in, network is the motor. Okay, the motor is the only device that is interacting with the zero sequence components, and you can see that is the series between 0.10 and 3 times 0.05. And here you can see that the equivalent, uh, mm, mm, the Thevenin equivalent impedance for zero sequence is 0.250. Okay. Finally, here in figure the 3.6, you can see that that is the zero sequence Thevenin model of my system. And well, that is all for this example. We create the sequence networks, and then we reduce the sequence models into the Thevenin equivalent model. Okay, what I'm trying to say, has been a very beautiful example, because allows you to understand that there is something big that is the sequence networks, and then there is something smaller that we can use for practical calculations and for interconnecting depending of the symmetrical fault, and that is the Thevenin equivalent model. Okay, please keep watching the videos, because this example will be used later in some other examples. Thank you very much for watching this video. Thanks again. Bye.